Hello, everybody. Today I'm going to be sharing with you Bleichenbacher's BB98 pattern oracle attack on PKC is number one, version 1.5. And to just give you a little bit background to this attack, it happened in back in 1998. Daniel Bleichenbacher, who used to work at the Bell's laboratory, he demonstrated a practical attack against a system using RSA encryption version 1.5, public key cryptography system number one, version 1.5. And he referred to that attack is being referred to mostly as a BB98. It's also being referred to as a pattern oracle attack version 1.5, and also some people call it a million messages attack, right? And one of the attack that Bleichenbacher uses is a chosen ciphertext attack, where an attacker chooses a ciphertext and send it to the victim, and the victim returns a plain text or some part of a plain text that can lead to the discovery of the encrypted message, and which also can lead to an adaptive cybertext attack, when the attacker can choose to send ciphertext depending on the previous one that he has sent, and then studied and reviewed. So I'm going to try and describe that, explain that attack, and then the attack surfaces, and then how we can mitigate that particular, or how they should have mitigated that particular vulnerabilities found that was exploited by the Bleichenbacher um, attack on RSA. So basically, RSA is normally used for encryption and decryption. Um, uh, um, and then uh, for a web-based application, normally it is SSL or TLS for encryption. So let me quickly demonstrate to you. There are two steps before a server and a client can communicate. There are two steps that happen. So first, they has to go through something we call a handshake, right? The handshake where they go and then agree on the protocols, how they're going to be communicating back and forth. And once they have agreed on it, then the next thing that follows is what the data exchange, where every communication between them is now encrypted. So that is where attackers or hackers try to come in between and act as a man in the middle and capture those packets and those information to be able to try it and decrypt it. And that is how Daniel Bleichenbacher came out with this attack. So let me quickly share my screen, and I'll show you the first phase of the handshake. So I have installed Wireshark on this computer, and I and this is my one of the interfaces on my computer here. So I'm going to start this capturing the packet here, and once I capture the packet, then I'm going to visit a website, and then we can study the handshake process. So I have started capturing the packet there. So let me go to this website here, Young IT Educators here, and try to refresh it. Let's see here, and it pops up. And as you can see, this website seems to it is encrypted and is certificate. It has a certificate there, and it said it is what secured connection. The connection is secure. So if we go back to our Wireshark, and then let's stop the capture here. Once you stop the capture, we can now focus on, we can filter for SSL or TLS information here. So once we find that, we can see that it start in the initial process where the client sent client hello to the server. And this information normally contains certain agreement that the client wants to establish with the server. And as you can see, it started off with version 1.0 TLS for the initial handshake, and then it converts it to 1.2 here. And also, one thing I want to show you is the cipher suite. Right? If you can see, the client is saying that I have all this cipher suite that I want to communicate with you, and then the server will, based on what the server has configured to use, it will choose one of these to respond. And this also comes with some information, some certificate signature algorithm that has been also agreed upon, that okay, I'm also you having this signature algorithm that I want to actually use. So when the server received that, then the server in response will also send a server hello back to the client, and then the server hello back to the client. Also, the server sent the certificate along with it. And if we look at the server hello that was sent back, um, we can see that it has the cipher suite that the server picked was TLS AES 3256, that the server picked to use to communicate with the client, with the one that the client has submitted to the server. So once that, I think maybe I should let me choose this one, because this seems to be where the certificate is involved as well. So the same thing goes here. So the client presents the cyber suite to the server, and then the server responds with a selected cyber suite. Okay, so in this instance, it's using RSA 256 encryption. Then the server sends back the certificate to the client, right? And that is a certificate that is going to be used in contacting the uh, in creating the secure channel, right? And then comes in the key exchange. That is where attacker wants to definitely hang around, and this is where they try to steal the information when it comes to what the exchange of keys, because that's when you exchange the public keys to be able to use to encrypt and then decrypt. Decrypt messages, right? So that is how uh, the RSA actually works. So the client will send a hello, and then the server will send a hello back with information saying, okay, you send me this, I have agreed to this, and this is how we're going to talk. And then they do the key exchange, and from that point onwards, once they has been established, then a data is start following suit with exchanging information between the two, the server and the client, right? So now let me share my screen, and then we can go into details as to how this attack happens. So I'm going to share my Blackboard here. Yeah. So Bleichenbacher exploited the format that RSA normally adapt for version 1.5. So this is how RSA adapted this kind of block format as a standard. So the first couple of bytes is a 00, which is a constant, and then a 02. So when the server receives a message and it conforms to this, then the server goes ahead to decrypt the message. And then from there is a pattern string, which is a pseudo randomly generated numbers that is being added to pad the string. Then right after that is the another byte of zeros, right? And then the following is the data block, is a data block. So this is the format that the PKCS version 1.5 uses in verifying that the request is actually following that particular format. So, for example, if we indicate that the block of data to be encrypted is D, right? Then these are the following steps that is going to be using. First is going to create a pattern string, right? It's going to create a PS based on a randomly generated number, right? And uh, uh, and and also it uses the key length, right? So this is the length of the block that is going to create. That is the length. So let's call that, let's say n, right? So from 0 to n, that is what is going to use to create it. And so k, so let's represent the k, which is the byte in length of n, right? So k is going to be this whole length here. Let's represent that with a k, right? um and then the first two bytes, as I've mentioned, those are the first two uh, bytes, 0, those are constant values, right? So if we're supposed to take these this byte and this byte and this byte, which seems to be constant out of here, then the key, the PS should be equal to the K, which is the length, the byte length of the key n, right? Minus those 3 bytes. So we have this byte here and this byte here and then this byte here, right? And then minus this data block here, right? This block, oh, I said I should call it a D. Erase here. Then that will give us what the length of the PS block, right? Of the pattern string, how much we need to be able to use to generate that, right? So once this PS has been determined, has been generated, right? Then you use that to encrypt the block form, right? So then you're going to have this byte here, then you're going to have this byte here, then you're going to have this that you just calculated with this occupying this space, and then this constant here, and then this absolute value of the, I mean, length of the block of data, right? Uh, so then once we have this, then we have to create our encryption block, right? Our encryption block, which is that whole thing, is going to be converted into an integer, and then we can call that integer what? X. So this particular integer X that has been generated or converted from this encryption block here is now going to be what? Encrypted with the RSA. So to be able to get our cipher here, so our cipher should be equal to this integer that we just computed, and by using what the encryption key, right? And then uh mod mod n, right? So basically, this is how you will be able to get your cipher. You will be able to get your cipher. So it goes through those kind of steps in general to be able to um, generate your cipher. All right. So once the receiver receives this message, then the receiver kind of reversely does the same thing, right? So let me clear up this space and then I can reuse this. So the receiver, once the receiver receives the ciphertext, then the receiver have to do this in reverse. So the receiver has to decrypt the cipher uh, uh, um, with the key, right? So let's call that integer x prime, right? So once he decrypts it, and he's going to get the x prime, and then he's going to convert that x prime into the encryption block EB prime to get EB prime. And once he get EB prime, then this EB prime is going to be representing that block that we just erased, with the first part being the first 2 byte being 00 and 02, and then the PS, and then 00, and then the block data, right? So when it gets to it, look at the first one and the first 2 bytes, and then he sees that, okay, this conforms. Then he goes and look for the other first byte of zeros after the PS, and then if he finds it, that will be the end of the PS, and it will be the beginning of the data, which is D. Um, right. So basically, that is how the RSA format works. So now, so this is how the requirement is supposed to, the check-in is supposed to be, right? So the EB, which is encryption block number one, has to be what? These 2 zeros, right? And then EB encryption block number two has to be what? This second byte here. And then encryption block number three all the way to what? Encryption block number 10. Remember the encryption, the PS can only go so much. So it goes from between number 3 all the way to number 10, which has to be a non-zero, right? So that's how you'll be able to differentiate between where this end. It has to be a non-zero, right? A non-zero. And then from EB11 all the way to N will be our block um, data, which is supposed to contain at least of 1 byte of double zeros, right? So this is how the requirement that it uses to classify whether it meets the information sent over, the cipher sent over meets this requirement. And if it meets the requirement, then it's accepted, and then it decrypts it, and then it's able to communicate. So one vulnerability that we see here is that, as we can see, is only checking to a conformity this of this block to the standard of PKCS version 1.5, right? So there's no integrity check here. There's no validation whether the information has been modified or not. So there's none of that. So that is one vulnerability that we can discover here as well. Okay, and So let me clear my board, and then so for the attacker to be able to do this, right? So the main goal of the attacker is to be able to get to the message, right? The attacker is hoping to get to the message, uh, and then the message, you see that the message, he has to definitely decrypt the decipher um, by using the mod of the whole key length, right? So there's the attacker's goal is to get to here. So if he has the ciphertext, he decrypts it mod n, and then he's able to derive this, right? So one thing that the attacker tries to do is that now he's going to create his own cipher, right? So let's call that cipher prime right here, and then he's going to use that same cipher, right, that he has as a man in the middle, right, and then he blocked it. He's going to use that, and then he's going to create his own cipher, and then he's going to encrypt that cipher using the same key length, right? Mod n, modulation n, right? And then he's going to send this to the Oracle server, and when the Oracle server gets it, Oracle server is going to try to first determine whether it fits this, if it conforms to this or not. If it doesn't conform to this, then it sends him error message back to the client, right? And once the error message get back to the client, which definitely is the attacker, then the attacker gets a little bit of information, either whole lot of information, or a little bit of information indicating that what it does not conform. So all that the attacker needs to do is that modify uh, uh, this value here, and then keep on trying again, and keep on trying, and keep on trying by modifying this number, by finding the range and modifying this number until he's able to get a conformity from the server that this particular one that you have produced conform to this particular the RSA PKCS version 1.5 format, right? So this attack is done in multiple phases. To be able to, for the attacker to be able to get this value here correct, he has to be working within a range, right? So that is the range that we're going to try to compute here. Let me clear up this board here, then we can. So the first step that the attacker, the first phase that the attacker uses is called blinding, right? So the blinding phase is where the attacker does not have the cipher, right? He doesn't have the cipher, and he's trying to come up with his own cipher, right? So for example, if you are given a certain number, an integer, right? Then you choose at random another integer. So let's say for example, you've been given an integer, let's say c, right, as an integer, and then you choose another, let's say another integer, let's call it s0, right, because this one is going to be incrementing as you go along, right? So you choose that one, and then you check this to make sure that it conforms to what, to the PKCS version 1.5 format, right? So once you have chosen this one, you've been given this as a random one, right? And then you choose a different one in such a way that your cipher, right, if you encrypt that and then you mod n, this should be able to conform to that format that we drew, right? Sorry, that format that we drew of the first 2 byte being zeros, and the padding string, and then the double the next byte being 0, and then the data as well. So that is the first step, right? So once you're able to get your first successful conformity, then you start from somewhere. Then you know that this number here, your cipher, definitely is getting closer to you, this equation right here. Let me even reuse this. So this one, because this is 0, once you're able to find the number, the integer, that definitely going to be, when you encrypt, is going to conform to this format. Then you know that definitely you are getting closer to that particular number, right? And then you are definitely also getting closer to your message, right? Your message. Oh, and then you can also represent that by an interval as well, right? So we take what 2b, 2b, which uh, I was playing a bit here, and you take the 3b, also 3b minus 1 to be your upper boundary, right? So this becomes what your interval, right? So you're going to choose an interval which is two of the block here. So you definitely chooses, let's take for example, if you have, and this is, so if you have a block here to n, right, and then you choose here and here, this is going to be your 2b block here, and then this is going to be your 3b block here, right? So then it says that after you have found your first number, that when you encrypt and mod it, and by the length is able to conform to this format. If it's able to conform to this format, then the interval should definitely be between this block here and then this block here, right? And it is the block minus 1. So definitely somewhere around here, right? And then going this way. So this should be what your range. So then at this point, we want to choose how we're going to increment this one. So let's say, for example, our first increment is just say 1. Let's start from 1, right? So then we're going to move on to the step 2. And in step 2, step 2 has a series of activities that you can perform, right? Step 2 has A, and it has B, and then it has C, right? The A is where you have chosen your initial I to be equal to 1, right? So all you need to do is then find the smallest integer. So let's say for A, we're going to find the smallest integer where that integer, right? Let's call it xi. So the next one, so we started with xo. So let's find out the next xi, which is the increment, right? That should be greater, right, than your key length divided by what? The 3b, right? Which is what this boundary here that we have set, right? So it has to definitely, this ci has to be what? Greater or equal to what? Half of what? Basically, you're trying to get to the middle of what? Of n, right here. Right. So once you have that, then you plug that into use that to encrypt that, and then you send it to the Oracle server, and then see if Oracle responds that it has met the requirement to conform to PKCS version 1.5. Right. In that instance, if it does not, where I is equal to 1, then the next step is going to try what? I is what? Greater than what? 1. because we already try I what equals to 1 and I is greater than 1. With this instance, you have what multiple um, multiple intervals, right? So when so in this one, you're going to choose an interval where m m this m here. Now we're going to move on to m, right? I minus 1, which is the next number below, right? It has to be definitely, at least it has to be equal to 2, right? Because this is what 1, and then we said our increment is going to be what 1. So if I is greater than 1, then the next logical number is 2. So then you find the smallest integer in such a way that for b, right, your si, remember your goal is to what, to discover what the xi which will what conform to RSA PK CS version 1.5 format, right? So your si should then be greater, right, in b here. Your isi should be greater than what, your si minus 1, right? Your si minus 1, right? And then after that, you just plug it into this equation right here. You encrypt it with si that you have chosen, which is number 2 you have chosen. Then you plug it in, and that mod says should be able to what, try and see if it conforms to this format, RSA format, right? So if it doesn't, then the next option is that this is where you have what, you're going to actually just use mi minus what 1 for this one, right? For the third option here, because this one you are looking at just a single integer, right? You're not looking at multiple ranges, right? Because for this one, where for option B here, we were looking at between what, two intervals, right? The upper and then the lower, right? So in here we trying to just get to only one interval, right? So when we, at this point, we want to also select what, at least and one interval, only this time only one interval, where if we take m I minus 1, then that should definitely be able to give us this interval right here, a to b, only that particular interval, right? So that will definitely get us very close. But because we have a and b here representing what, getting us closer to the message, then we have to also find different values, integer values, that will definitely help us to reach SI goal here that we want to find. We want to find that particular integer that when we plug in here. So now we know that this message, uh, the single interval is definitely going to get us very close, because as we keep on approaching, if we find out that this is just a single interval here, the only first interval here, then definitely this corresponds to what, that message that we are looking for, right? So the goal is to just get closer. So once we have I minus 1, we want to find series of integers, right? So let's call that one r. The people call it ri. So let's call that ri, right? And then your goal is that ri should definitely be greater or equal to what, your 2, remember your 2b, right? Your 2b, and then your si minus 1, right? Because we already consider what, the si minus 1 for what, option B here, right? So your 2b should definitely be greater than your ROI should definitely be greater or equal to 2b minus 1, and then minus what? This 2b, and then divided by what? The whole length, right? So this is the goal here, is that if you're able to find an integer that falls within this range, then you can plug this one in such a way that, let me erase this part because I don't think I need this part anymore. Then you'll be able to definitely get to the point where your SI that you are looking for, right, would definitely have to be what? Less than your 3b plus this this integer that you have what? You have represented, right? Ri times the key length, right? And then divided by your first, oh, I erase it, the interval that we have. Remember, we have mi interval minus 1, which we have narrowed down to only a and b, interval between a and b here. So this should definitely be divided by what? Um, by your lower boundary, right? It has to be, SI has to be less than this, and SI has definitely to be what? Greater or equal to your 2b plus your same integer that you are looking up for here, right? Ri times n, which is your length, divided by what? Your upper um, um, interval, single interval, right? So this is your end goal, to be able to get to your single message here, right? So now you're going to use this to calculate, to get that integer, that SI, right? So in this case, just like here, you have this 2b here, you have 3b here, right? And then you pick out an integer in such a way that is probably going to be around here, or maybe around here, right? So from here all the way to here is a possible range, but you want to narrow it down in such a way that you be only pick up only a single block that represents your SI, and then that will help you discover your message, right? So the attacker will just continue doing this and sending it, and then plugging this back into this to encrypt with a key, right? Once you find SI, plug SI in here, encrypt mod n, and then send it to the Oracle server. And then if Oracle server is able to confirm that it conforms to this format, then it gives an attacker an upper hand, right? So the goal here from step A, B, and C is to find what? SI, that particular sweet spot, right? That particular integer that will help to be able to identify that it conforms to this, right? So once you're able to find that, so for example, if we're able to find that, okay, SI is somewhere between here, right? If that is the goal, then we have to plug that into the next step 3 equation. Once you find SI, right? Let me erase some of this so I can reuse the board. I think I will need this. I don't need this. So once you are able to get to that particular SI here, right? Then you are getting closer to MI, right? Then you start picking up what? Integer, let's represent that by, let's say, B, A, B, and R, since we use R before, right? Those are your integer values, right? Then you're going to plug them into this, and then you're going to find the maximum of what? Your A. Remember, we have chosen the oh, I erased it again, right? Where we have gotten to only one single interval, right? So you're going to choose that, and then you're going to look out for what? The maximum of that interval, and then you look out for what? The ceiling. You use that to find the ceiling of the 2b plus your R and then N, right? Divided by what? This sweet spot that you have identified, right? Your SI, that integer that you have identified. You take the ceiling of that, and then um, that will be your interval. And then you do that the same thing for what? For the minimum, you take the minimum of the upper part of the interval, the constant interval, and then you take the floor of 3b, right, minus 1. Remember, this is 3b minus 1 right here. And you add it to your Rn, and you multiply by your Rn, and then you divide by your single integer that you have come out with. Yeah. So once you plug this in here and you're able to come out with the integer, right? Then you plug your integer uh, 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 back in, and then that will definitely help you. So in here, you are getting very close, right? So this is N here, and this is O here, right? And now you have narrowed down, right, your two B's, which is the ceiling of your 2B, right? Which is going to be right here. And then your 3B. And then the floor of your 3B, which is going to be around here, right? So now this part becomes what? Your focal point of identifying your message, where your message is, right? So then you know that definitely your message is falling between what? A and B, which is what? A and B here, right? And then you know also that your R is definitely going to fall in between your R should definitely right here. Your R should should be um should be less than or equal to your B here, your B with your SI, right? Minus your 2B, and then divided by your N. And then your R should also be greater or equal to your A here, SI minus your 3B minus 1, right? 3B minus 1, and then divided by N, right? So once you're able to get your R to be in this range, you know definitely this is the range. And once you plug that in, you should be able to find exactly in between here where the message corresponds to. And that will be your message. And then that will definitely lead you to your step 4, which is what? your message that you have derived, and that will bring you to M, which is definitely going to be very close to your cipher being decrypted, right? So if it's not, then you have to increase SI. If it does, if you get to step 4 and does not is not very close to the message is not very close to your cipher and then your decryption key, then you have to increase your SI, right? SI plus 1, and then you go all the way to step 2, and then start from here, from A again, and then rediscover, recompute again, and then it goes on and on until you're able to find to find that, right? So now, so this is how different the attacker goes about. This is how the Daniel Bleichenbacher, that's how he went about. He made a little bit of assumption and a little bit into the calculation, calculated the calculation, but definitely that is how the attack happens, and that is how he was able to exploit it. But now the question, what are the vulnerabilities that this process took advantage of, right? There are multiple vulnerabilities that I can think of, and those vulnerabilities include, let's say, the RSA encryption is definitely vulnerable to an integrity check, right? So because when the message is sent to the server, right, all the server is checking is that it conforms to this, right? So let me check. It doesn't have the first byte to be 0. Doesn't have the second byte to be 02, right? Doesn't have the another constant 0. If it does meet though, then it says, okay, you are good to go, right? So it doesn't do any integrity check. So that is one vulnerability there, right? And also another vulnerability that I can think of is Oracle is also vulnerable to the integrity check as well, because Oracle server is not doing any validation as well. And also the pattern here, the PS string here, uh, 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 that is also um, vulnerable, because this is being a pseudo random number being generated here. But if the number being generated is not random enough, then the attacker can definitely regenerate this to basically reconstruct this whole thing by himself, right? And also another vulnerability that I see here is a timing attack here, where the attacker constantly monitors how long it takes the server to respond, right? So if the server should respond, let's say the server checks the first time and said, oh, it does not conform, then the server sent a message, an error back to the server, to the client, then immediately the attacker is going to know that, okay, for this particular time, it did not conform, and it took this long for the server to respond, right? So if it takes a little bit longer, then the attacker is going to know that, of course, this particular integer that I have is able to go past a certain point. So by so doing, the attacker is able to study and know what kind of attack uh, they can uh, they can string together to come and attack you. And also the other vulnerability that I could think about was that, definitely, as I mentioned, that there's a possibility that there's going to be a man in the middle attack, right? So you have Oracle here, Oracle server here, and then you have the client here, right? And then they keep on sending messages, the handshake going on here, right? And then there's going to be the attacker here, right, sitting in here, and all that he's doing is just intercepting and this message here. And once he intercepts it, then he has the leeway to definitely either he passively decrypt himself and then try to find what is going on, or he actively just monitors and see what information is being sent around, or how he can definitely leverage that vulnerability, right? Now, the question is which system did it target to be affected to attack for this Bleichenbacher attack? And of course, as I mentioned, this is a Oracle server, and Oracle is the one that communicate with the client. So definitely is the Oracle server in play here. And the other question is, could it be modified to spread to other system? And the answer is yes. So actually, there's been several attack even after the 98 BB98 Bleichenbacher's BB98 attack, right? So another way that it could be exploited is that the attacker could work on a lower exponential RSA integer, where you just pick a smaller bit of number, and because a smaller bit of number, he could probably be able to constantly get a little bit of information from the server to be able to construct the data together, right? And then the another attack also could be that uh, um, because of the constant response from the server, right? The attacker could definitely use that to reconstruct the attack again, so that you know that, okay, at this particular time, if I send this, if it's wrong, it takes this long. If it's right, it takes this. So it basically just be responding back to the attacker, and then the attacker is able to reconstruct um, the attack again, right? Uh, so now the other question is, what countermeasures were taken, or could or should have been taken? Of course, definitely, as I've mentioned, the uh, Oracle has to implement some form of integrity check, or RSA has to implement some form of integrity check on the format conformity to PKCS version 1.5, right? And actually, they have, because they have moved to a different version, RSA OAEP, which definitely has some integrity check, and then it mitigates this vulnerability, right? And also, another thing that we can do to mitigate is that Oracle has to stop sending an immediate response back to the server. So what could possibly happen, could be done to mitigate, is that the attacker, because he's getting constant feedback, he's reusing that feedback. So what the Oracle server could do is that if only it does not conform, right, then it should send a generic message, right? And also, to be able to overcome the timing, he should just wait. Even if it doesn't conform, he should wait until it has reached the encryption's end, where is decrypting end, where is decrypting, and then if it fails, when everything has finished, then send up a generic message back to the client or back to the server. And then that way, the attacker is not going to have too much information, right? And then he's not going to be able to know at what point did the attack fail, right? So that is how we're going to be able to mitigate these um, um, vulnerabilities. And of course, there's been several algorithms, RSA algorithms that has been in play since the BB98. And even though other people still keep on using 1.5, that is how come the attack keep on resurfacing itself. So I guess the best mitigation is to move on to a well tested and documented RSA version. So that ends my presentation. Thank you for your time. Bye. Here's the reference that I use. Daniel Bleichenbacher Wikipedia page, and this is a RFC 3447, and then his Daniel Bleichenbacher's research paper is a reference to it. All right. Thank you.